Welcome. Today, we're going to tackle a fascinating algebraic challenge. We're going to learn how to solve the equation x cubed plus y cubed plus z cubed minus 3xyz equals 1. This might look daunting at first, involving 3 variables to the third power. But by the end of this video, you will be able to recognize and factor a special type of expression called the sum of 3 cubes, and then use that factoring to find all integer solutions to this equation. So, our main goal is to factor the sum of 3 cubes and use it to solve this specific equation. Let's start by focusing on the expression on the left-hand side of our equation. This expression is called the sum of 3 cubes, or sometimes an identity. Our first objective is to factor this expression into a simpler product. This is a very common technique in algebra for solving equations. To do this, we'll use another well-known identity, the sum of 2 cubes. You may recall that x cubed plus y cubed equals the quantity x plus y times the quantity x squared minus xy plus y squared. This identity shows us how to factor the sum of 2 cubes into a linear term and a quadratic term. This is a fundamental identity that we'll leverage. Let's apply this to our expression. We can group x cubed and y cubed together. Applying the sum of 2 cubes identity, we get the quantity x plus y times the quantity x squared minus xy plus y squared, and we still have the plus z cubed and minus 3xyz. Now we can see another structure. Let's call the term x plus y our new a and z our new b. We have another sum of 2 cubes, a cubed plus b cubed. Let's rewrite the expression to highlight this. We have the quantity x plus y cubed plus z cubed, and then the original terms are adjusted. Let's simplify the original expression further. The term x plus y x squared minus xy plus y squared is equal to x cubed plus y cubed. So we have x cubed plus y cubed plus z cubed minus 3xyz. We want to factor this into something involving x plus y plus z. It turns out the complete factored form is the quantity x plus y plus z times the quantity x squared plus y squared plus z squared minus xy minus yz minus zx. This is a key identity, and it's our first objective accomplished. We have successfully factored the sum of 3 cubes. This is a powerful tool we'll use in the next step. Now that we have the factored form of the sum of 3 cubes, let's substitute it back into our original equation. Our equation was x cubed plus y cubed plus z cubed minus 3xyz equals 1. Replacing the left-hand side with its factored form, we get the quantity x plus y plus z times the quantity x squared plus y squared plus z squared minus xy minus yz minus zx equals 1. This is a much simpler form to work with, especially when we're looking for integer solutions. Notice we have a product of 2 integer factors that equals 1. In integer arithmetic, there are only 2 ways for this to happen. Either both factors are positive 1 or both factors are negative 1. Let's analyze the second factor more closely. This will be key to simplifying our problem even further. Consider the quadratic factor, x squared plus y squared plus z squared minus xy minus yz minus cx. What can we say about its value? Let's try to rewrite this expression. We can double it to make the algebra easier. Now, let's group the terms to form perfect squares. This gives us the quantity x minus y squared plus the quantity y minus z squared plus the quantity z minus x squared. Therefore, our factor f is equal to 1/2 of that sum of squares. Now, let's think about the properties of squares. The square of any real number is always non-negative. It's either positive or 0. So, since f is a sum of squares, f must always be greater than or equal to 0. If f were negative, say minus 1, it would require a sum of non-negative numbers to be negative, which is impossible. We're almost there. We have 2 cases. But our analysis of the quadratic factor, which we called f, helps us eliminate one of them. Recall our 2 possible cases for solving the equation. We just proved that the factor f must be greater than or equal to 0. Let's write that down as a reminder. Now, let's look at case 2. In this case, it states that f equals negative 1, but we just showed that f cannot be negative. This means that case 2, where f equals negative 1, is impossible in integers. It provides no valid solutions. This leaves us with only one possibility. Case 1. The sum of the variables, x plus y plus z, must equal 1, and the quadratic factor f must also equal 1. This is a huge simplification. Instead of one complicated cubic equation, we now have a system of two much simpler equations to solve. We have successfully reduced the problem. So, our task has been simplified to solving the system. Equation 1, x plus y plus z equals 1. Equation 2, x squared plus y squared plus z squared minus xy minus yz minus zx equals 1. Let's focus on equation 2 for a moment. We already found an alternative form for it. We know that x squared plus y squared plus z squared minus xy minus yz minus zx is equal to 1/2 of the quantity x minus y squared plus y minus z squared plus z minus x squared. Since the expression equals 1, we can set them equal to each other. 1/2 times the sum of squares equals 1. Multiplying by 2, we get the quantity x minus y squared plus the quantity y minus z squared plus the quantity z minus x squared equals 2. We are looking for integer solutions. The only way for a sum of 3 perfect squares to equal 2 in integers is if 2 of the squares are 1 and the third is 0. This is a powerful constraint. This leaves us with 3 distinct possibilities. Either the first 2 differences are plus or minus 1 and the third is 0, or the second 2, or the first and third. Let's work through the first case based on our sum of squares equation. We'll set x minus y squared equal to 1 and the other 2 terms equal to 0. Case A, let x minus y squared be 1, which means x minus y is plus or minus 1. Let y minus z squared be 0, which means y minus z is 0, or y equals z. And let z minus x squared be 1, which means z minus x is plus or minus 1. The last constraint, z minus x equals plus or minus 1, isn't new. Since z equals y and y minus x equals plus or minus 1, it automatically follows that z minus x equals plus or minus 1. So the first equation is sufficient. We have x minus y equals 1, and y equals z. Now we combine this with our first equation from the system. X plus y plus z equals 1. We have the system of equations, x equals y plus 1, and y equals z, and their sum is 1. Substituting, we get y plus 1 plus y equals 1, which simplifies to 3y plus 1 equals 1, or 3y equals 0. This gives us y equals 0. Since y equals z, z is also 0. And since x equals y plus 1, x is 1. This gives us the solution set 1, 0, 0. This was the case where x minus y was positive 1. What if it was negative 1? If x minus y is negative 1, we follow the same process and find the solution is 9/3, 2/3, 2/3, which is not an integer solution. So, we found one integer solution, 1, 0, 0. But is that all? Not quite. Remember our constraints from the sum of squares. We had 3 possibilities for which pair of differences could be 0. We just solved the case where y equals z. By symmetry, the other cases will give us more solutions. Let's explore these by applying the same logic as before. The process will be identical, just with the variable swapped. Case B, let x equal y. Our system becomes x plus z equals 1. The solution is x equals sign, y equals sign, z equals sign 1/3, not integers. In this specific case, the differences must have been xy equals sign 0, and y minus z quo 0 plus 1, and z minus x quo 0 plus 1. Let's see what happens if yz equals sign 1, then y equals z plus 1. Since x equals sign y, x equals z plus 1. Substituting into x plus y plus z equals sign 1 gives z plus 1 plus z plus 1 plus z equals sign 1, or 3z plus 2 equals sign 1, so z equals sign 1/3. Again, not integers. Wait, I made a mistake. If x equals sign y, then the difference, xy squared, is 0, not yz. Let's be careful. The correct constraints from our sum of squares equation for x equals sign y are x equals y and yz squared equals 1. If y minus z equals 1, we get the solution 0, 1, 0. If y minus z equals minus 1, we get 2/3, 2/3, negative 1/3, which is not an integer. Ah, I made another error. Let's start with x equals sign y, and then use the possibilities for the remaining 2 terms. If x equals y, then x minus y is 0. This forces the other two terms in our sum of squares equation to be 1 each. So y minus z must be plus or minus 1, and z minus x must be plus or minus 1. Let's assume y minus z is 1, and z minus x is 1. This gives y equals z plus 1, and z equals x plus 1. Substituting x plus 1 for z in the first equation gives y equals x plus 2. Since y equals x, this implies x equals x plus 2, which means 0 equals 2. This is impossible. Let's try y minus z is 1, and z minus x is minus 1. This gives y equals z plus 1, and z equals x minus 1. Substituting z equals x minus 1 into the first equation, we get y equals x. This is the condition we started with. So we need to solve the system x equals y, z equals x minus 1, and x plus y plus z equals 1. This gives us x equals 2/3, which is not an integer. So it appears that if x equals y, there are no integer solutions. Let's recheck this. If x equals sine y, then xy queried equals 0. So we need yz 2 queries plus zx queried equals 2. This means yz must be plus or minus 1. If yz equals 1 and zx equals minus 1, then y equals z plus 1 and z equals x1. Substituting the second into the first gives y equals x minus 1 plus 1 equals x. This is consistent. The system is x equals sine y, z equals x minus 1, x plus y plus z equals sine 1. Substituting gives x plus x1 equals sine 1, or 3x equals sine 2. No integer solution. My apologies for the confusion. Let's look at the remaining possibility based on the sum of squares. xy is plus or minus 1, yz is 0, zx is plus or minus 1. This gives us y equals sine z, which is what we solved initially, giving the solution 1, 0, 0. The other two symmetric cases would be 1, x equals sine z, which leads to the solution 0, 1, 0. 2, x equals sine y, which leads to the solution 0, 0, 1. Let's verify these. If x equals sine z, and xy queries equal to 1, and yz queries 1, and zx queries 0. So we have x equals sine z, and xy queries 1, then x equals y plus 1. The sum is x plus y plus z equals y plus 1 plus y plus 1 equals 3y plus 2 equals 1. So 3y equals sine 1, not integer. Let's look closely at the conditions for the three solutions. In our first solution, y equals sine z. The differences are xy equals sine 1, yz equals sine 0, zx equals sine 1. In our sum of squares equation, 1 dequared plus 0, dequaris minus 1 dequared equals 1 plus 0 plus 1 equals 2. This works perfectly. By symmetry, the solution 0, 1, 0 comes from z equals sine x. The differences are xy equals sine 1, yz equals sine 1, zx equals sine 0. The sum of squares is minus 1 queries plus 1 queries plus 0 equals sine 2. Also correct. And the solution 0, 0, 1 comes from x equals sine y. The differences are xy equals sine 0, yz equals sine 1, zx equals sine 1. The sum of squares is 0 queries plus minus 1 queries plus 1 equals 0 plus 1 equals sine 2. Correct. So, we've carefully found all the integer solutions. Let's summarize what we've discovered. We started with the equation x cubed plus y cubed plus z cubed minus 3xyz equals 1. Our first key step was to use the identity for the sum of three cubes to factor the left-hand side. This identity, x plus y plus z, allowed us to turn a complex cubic equation into a system of two simpler equations. The second crucial step was analyzing the quadratic factor and rewriting it as a sum of squares. This form, 1/2 times the sum of squares, proved that the factor must be non-negative. This was essential for eliminating one of our two cases. This left us with the system of equations. X plus y plus z equals 1, and the sum of the squared differences, xy squared plus yz squared plus zx squared, equals 2. By finding the integer possibilities for the differences and solving the resulting systems, we found all the integer solutions to the original equation. The three integer solutions are 1, 0, 0, 0, 1, 0, 0, and 0, 0, 1. And by symmetry, we can also say that any permutation of these, like 1, 0, 0, or 0, 1, 0, or 0, 0, 1, are all valid solutions. And this concludes our exploration. We've successfully achieved our goal of factoring the sum of three cubes and using it to find the integer solutions to a challenging cubic equation. Thank you for watching.